This session is called Database and SQL. Today we will answer three simple questions. First, what is a database and why do analysts rely on it? Second, what is a database management system, the software that protects and organizes the data? Third, how do we use SQL, the standard query language, to read and change data in a safe and repeatable way? By the end of class, you will understand the basic ideas behind tables, keys, and constraints, and you will be able to run, create, read, update, and delete operations using a notebook. We will practice in Google Colab with DuckDB, which runs fast on your laptop with no setup. Please follow along, ask questions at any time, and focus on the concepts first. The code will make sense once the ideas are clear. Let us begin with the difference between a database and a DBMS. Before we write any SQL, let us make one clear distinction. A database is not the same thing as a DBMS. A database is the organized collection of data. Think of tables filled with rows and columns. That is the content. A DBMS, which stands for Database Management System, is the software that manages that content. It defines tables, stores the data safely, lets us run queries, controls who can see or change information, and helps us recover after failures. Here is an easy analogy. Imagine a library. The books on the shelves are the database. The librarian and the catalog system together are the DBMS. Books equal data. The catalog rules that say where each book belongs equal the schema. The librarian who finds and returns books quickly is like the engine that performs work. On this slide, you can see three core pieces of a DBMS. First, data. These are the values. For example, customer identification number, product price, or the date an order was placed. Second, schema. This is the structure or the blueprint. It names tables and columns, sets data types, and defines rules. For example, an email must be unique or an order item must point to a valid order. These rules keep data consistent. Third, engine. This is the part that processes work. It reads and writes files, chooses a query plan, uses indexes, and handles transactions so that many users can work at the same time without stepping on each other. Why does this distinction matter? When we say we will store something in the database, we are talking about the data itself. When we say we will create a table, run a query, or grant access, we are using the DBMS to manage that data. SQL is the language we use to talk to the DBMS about how to organize and retrieve the database. So which one enforces a unique email rule, the database or the DBMS? The answer is the DBMS using a schema constraint. In this course, we will use DuckDB as our DBMS inside Google Colab. The tables we create inside it will be our database. Now let us move on to where SQL fits into this picture. Let us look at how a relational database is organized. On the left is the customers table. Each row is one customer. The first column, customer underscore ID, is marked primary key. Primary key means every row must have a unique identifier. The email column is marked unique, which means no two customers can share the same email address. On the right is the orders table. Each row is one order. Here order underscore ID is the primary key for orders. The customer underscore ID column is marked foreign key. Foreign key means this value must match an existing customer underscore ID in the customers table. Follow the arrow from customers.customer underscore ID to orders.customer underscore ID. That link is called referential integrity. It guarantees that every order belongs to a real customer, not a random number. Now a quick note about the language we use. SQL is declarative. You describe what result you want. For example, join customers to orders, and the database engine decides how to do it efficiently. Finally, constraints protect data quality. Primary key enforces unique identity. Foreign key enforces valid relationships. Not null requires a value. Unique prevents duplicates. Check enforces custom rules, such as price must be greater than 0. This is the core idea of relational databases: well-defined tables, clear keys, and rules that keep data consistent. Now we will talk about 4 promises that reliable databases try to keep. The 4 letters are ACID. They stand for atomicity, consistency, isolation, and durability. Atomicity means all or nothing. Either the whole transaction completes or none of it does. Think about a bank transfer. The system must write both the debit and the credit together. If anything fails, the system rolls back the entire change. In short, commit everything or roll back everything. Consistency means rules are preserved. After any transaction, the data still follows all constraints and business rules. For example, an order item cannot point to an order that does not exist. Primary keys, foreign keys, not null rules, unique rules, and check rules all help keep the data consistent. Isolation means no interference. When many users work at the same time, their transactions should not step on each other's work. For example, 2 customers checking out at the same time should not oversell the last item. Databases offer isolation levels such as read committed, repeatable read, and serializable to control how strict this protection is. Durability means the change survives failures. Once the system commits a transaction, the data stays saved even after power loss or a crash. For example, confirmed orders are still there after a server restart. Techniques like write-ahead logging, checkpoints, and backups make this possible. These 4 ideas explain why we can trust relational databases with important work. With ACID in place, we can use SQL to update data safely and sleep well at night. Let's take a quick look at the database engines you are most likely to encounter. DBMS stands for Relational Database Management System. These are the software tools that store data in tables, enforce rules, and let us run structured query language. On the industry side, 5 engines appear again and again. PostgreSQL is a very popular open source database known for stability and advanced features. MySQL is another open source database often used in web applications. Microsoft SQL Server is a commercial product that is common in large companies and enterprise systems. Oracle Database is another commercial option, very powerful but often expensive. SQLite is a small embedded database useful when you want the database bundled inside an application or on a mobile device. For our class, we will use DuckDB. DuckDB is lightweight, column-oriented, and designed for analytics. The key advantage is that it runs directly inside a notebook without a separate server. That means you can practice structured query language in Google Colab with almost zero setup. Keep in mind that although the engines differ in performance, licensing, and features, the structured query language you learn here will transfer across them. Once you are comfortable writing queries in DuckDB, you will be able to adapt easily to the other systems. Let's study about when we reach for NoSQL systems. There are 3 common reasons. First, flexible schemas. Your records do not all look the same, and you want to store fields that may appear or disappear over time. Second, horizontal scale. You expect very large volumes of reads and writes across many machines. Third, specialized access patterns. You design for a few specific query shapes instead of many complex joins. Now look at the triangle on the right. It shows 3 goals: consistency, availability, and partition tolerance. We call this the CAP triangle. Consistency means that all users see the same data after a write. Availability means the system keeps answering requests. Partition tolerance means the system keeps working even when the network splits machines into islands. During a real network partition, a system cannot fully achieve all 3 goals at the same time. It must favor consistency or it must favor availability while still tolerating the partition. Here are simple examples. If you are serving a social feed or a cache, you often favor availability with partition tolerance. Users keep getting responses even if a few updates arrive slightly later. If you are handling orders or inventory, you often favor consistency with partition tolerance. You would rather delay a response than sell the same item twice. Consistency and availability together are common when everything sits on a single machine or inside one rack, where partitions are very rare. This triangle is a simplified mental model. In practice, many NoSQL systems let you tune behavior per operation. You can ask for strong consistency on a write that really matters, and faster eventual consistency on a read that can be a little stale. The main takeaway is this: choose the trade-off that matches your workload and be explicit about it. Now let's map common NoSQL types to real use cases. First, document stores. Use these when record shapes vary. A customer profile today might have 5 fields, and tomorrow it might have 12. Documents often look like JSON. You get flexible fields and rich queries, but joins across many collections are limited. Examples include MongoDB and Couchbase. Second, key and value stores. Use these for ultra-fast lookups by a single key. Typical cases are session stores, feature flags, leaderboards, and caching. Operations are simple and predictable. There are no joins. Examples include Redis and Amazon DynamoDB used in key and value mode. Third, wide column stores. Use these for very large write and read workloads with predictable access patterns, such as event streams or time series. Data is partitioned by keys across many machines. Many systems let you tune read and write consistency per request. Examples include Apache Cassandra and HBase. Fourth, graph stores. Use these when the main job is to traverse relationships, such as recommendations, social connections, or fraud rings. Data is modeled as nodes and edges, and path queries are very fast. Examples include Neo4j and Amazon Neptune. How should you choose? Start from your query patterns and your scale targets, not from the brand name. Pick the store that fits the shape of your data and the way you plan to access it. Remember that many platforms let you tune consistency and durability so you can balance speed and safety. Quick check. If your team needs a real-time feed with millions of reads per minute, which type would you test first? Likely a key and value store with a cache. If you need multi-hop recommendations such as friends of friends, you would test a graph store. On this slide, we will compare relational systems and NoSQL systems at a high level. Think of 3 questions. How is the data structured? How do we query it? And what kind of consistency do we get? First, structure. In a relational database management system, the schema is fixed and strongly typed. We define tables, columns, and constraints up front, and we keep the design normalized. In NoSQL, the schema is flexible. Records can vary in shape, which is helpful when fields change over time or when different items need different attributes. Second, queries. Relational systems are great for rich joins and multi-table transactions. They also support strong ad hoc analytics because you can combine tables in many ways. NoSQL systems are optimized for specific access patterns. You often look up by a key or read from a single partition table. Joins are limited or handled in the application, which keeps reads fast and predictable. Third, consistency. Many NoSQL systems offer eventual or tunable consistency. You can choose stronger guarantees for critical writes and looser guarantees for speed on less critical reads. How should you choose? Start with the shape of your data, your common query patterns, and your scale goals. Do not choose based on hype or brand names. Many real projects blend both approaches. Use a relational system for core transactions and reporting, and use NoSQL for feeds, sessions, and caching where flexible schema and very fast reads matter most. Quick check. If you need complex joins across several tables, which side fits better? The relational side. If you need millions of key lookups per minute with simple reads, the NoSQL side is often a better fit. Structured Query Language, or SQL, plays four main roles. It lets us query data, manipulate data, define the schema, and control permissions and transactions. First, DQL, Data Query Language. Purpose: read and filter rows. You will say things like select name and price from products where active equals true. Most of your day-to-day analytics start here. Select, filter, sort, and preview results. Second, DML, Data Manipulation Language. Purpose: insert, update, and delete rows. Examples include insert a new user with an email, update a user to set active equals false where the identification equals 5, and delete from users where the identification equals 5. Safety rule: before any update or delete, run the same where clause as a select to confirm which rows will change. Purpose: create and change the schema. You design tables and columns and constraints. For example, create table users with identification integer primary key and email text, or alter table users, add column created underscore at timestamp, or drop a temporary table when you are done. Think of DDL as the blueprint for your database. Fourth, DCL and TCL, Data Control Language and Transaction Control Language. Purpose: permissions and transactions. Examples: grant select on products to analyst, revoke update on users from trainee. For transactions, commit to save changes, rollback to undo changes if something goes wrong. A quick rule of thumb: you will write select the most, insert and update quite often, create or alter when designing, and grant, revoke, commit, and rollback as needed for security and reliability. In this course, we will practice all four roles in Google Colab with DuckDB, so you will see how they fit together in real workflows. Based on what we studied so far, let's practice SQL using our Colab file. SQL stands for Structured Query Language. It is a standard language made to manage and work with relational databases. In plain words, SQL helps us ask for data, change data, and shape the structure of our tables. We will use it all through this course. SQL does 5 main jobs. First, data querying. This means reading data with questions called queries. Most of our daily work is here. We use the word select to fetch rows that match certain conditions. Second, data manipulation. This means adding, changing, or removing rows. The core commands are insert, update, and delete. Before any update or delete, we will preview with a select to make sure we are touching the right rows. Third, data definition. This is how we create and change the structure of the database. We use create, alter, and drop to define tables, columns, and other objects. Fourth, data access control. This sets who can see or change data. We use commands to grant or revoke permissions so that analysts and applications have the right level of access. Fifth, transactional control. This protects data when multiple changes happen together. We group changes into a transaction and then commit to save or roll back to undo if something goes wrong. This keeps our data consistent and trustworthy. In today's lab, we will practice these ideas inside a notebook. We will connect to DuckDB and use JupySQL so we can write SQL directly in cells, see results instantly, and build good habits from the start. Let us begin with a quick select to make sure everything is working. First, we will make a tiny table in Python. Then we will connect SQL to our notebook with DuckDB and JupySQL. Part 1. Build a tiny table with pandas. Line 1 says, import pandas as PD. This loads the pandas library and gives it the short name PD. Pandas is a tool for working with tables. Next, we create a small object named data. It has 3 keys: name, age, and occupation. Each key maps to a list. For example, the names are Alice, Bob, and Charlie. The ages are 25, 30, and 35. The jobs are engineer, doctor, and artist. Think of each key as a future column and each position in the list as a future row. Then we build a table in memory. df equals pd.dataframe of data. A data frame is Panda's word for a table. After this line, df holds 3 rows and 3 columns. Finally, we just write df on its own line in a notebook that displays the table so we can see it. Part 2, set up DuckDB and JupySQL so we can run SQL in cells. Cell 1 installs our tools from Python's package manager. Let's wait till all the packages are completely installed. Cell 2 loads the libraries into Python and enables the SQL magic. The phrase %load_x turns on the SQL commands inside the notebook. Cell 3 creates a database connection and gives it a short nickname. The last line means tell JupySQL that when we say DuckDB, we mean this connection. From now on, any cell that starts with %SQL will run SQL against DuckDB. Cell 4 is optional but helpful for demos. It measures how long each cell takes. Now, the notebook will print the elapsed time after each cell, which helps us compare queries later. At this point, our environment is ready. We have a small pandas table we can register as a temporary table. We have DuckDB running inside the notebook, and we can use %SQL to write real structured query language. Before we write real queries, a few basic rules. First, structured query language statements are made from descriptive keywords and commands. Think of them like short sentences that the database understands. Second, each query should end with a semicolon. In notebooks, it sometimes works without it, but using a semicolon is a good habit because most tools expect it. Third, structured query language is not case sensitive, but we follow a readability convention. Uppercase for keywords like select and from, and lowercase for identifiers like table names and column names. In the demo cell, we run one tiny query that returns the text, hello structured query language, and labels the column as greeting. This cell is just to confirm our environment is working and to show the basic shape of a statement, keyword, what to return, and a semicolon. Next, the most common data types you'll see in tables. Integer, whole numbers without decimals. We use this for counts, identification numbers, and ages. If you do not need fractions, use integer. Decimal, numbers with decimals where precision matters, such as prices, exchange rates, or percentages you will calculate with. Decimal avoids rounding surprises. Varchar, which stands for variable character. Text strings such as names, emails, product codes, or campaign identifiers. Variable means the length can change up to a limit you set. Date, calendar dates. This makes it easy to filter by day, month, or year, and to do time-based analysis like week over week or month over month. Boolean, true or false, great for yes or no flags such as active, opted in, or is premium. A quick tip for analytics. Choose the tightest data type that fits your data. Integers and booleans are compact and fast. Decimals protect money and metrics. Varchar is for text. Date keeps time logic clean. Getting types right now prevents many errors later. Think of a schema as the blueprint of your database. It answers 2 questions: how the data is organized and how pieces of data relate to each other. We are not talking about the actual rows here. We are talking about the design. First, tables and fields. A table is like a spreadsheet for one kind of thing, such as customers or orders. Each table has fields, which are its columns. Every field has a data type, such as integer, decimal, text, date, or boolean. Data types set the rules for what can go into that column. Second, relationships. Relationships explain how one table connects to another. For example, one customer can have many orders. We create a primary key in the customers table that uniquely identifies each customer, and a foreign key in the orders table that points back to that customer. This link makes joins possible and prevents orphaned records. Third, indexes. Indexes are like fast lookup guides. If you search by email all the time, you can create an index on the email field. Queries that use that field will run much faster. The trade-off is a little extra storage and slower writes because the index has to be updated. Fourth, constraints. Constraints are rules that protect data quality. For example, not null means a field must have a value. Unique means no duplicates. For example, one email per customer. Primary key enforces a unique identifier for each row. Foreign key enforces valid links between tables. Check can enforce a custom rule, such as price must be greater than 0. In this cell, we do two things. We open a small database in memory and we create a table called users. First, we make a connection with DuckDB to an in-memory database. In-memory means the database lives only while this notebook session is running. It is fast and perfect for practice, but it will not persist after we close the session. Second, we send a create table command through the connection. We create a table named users with 3 columns. ID as an integer number, name as variable length text, and email as variable length text. This is the minimum structure we need for simple demos. Now we will add a few rows to the users table. This cell sends one insert statement to the database. We name the columns in the order we want, ID, name, email, and then provide the values for each new row. We show 2 rows at once by separating them with commas inside the values list. 2 best practices to remember. Always list the column names in the insert. That way, if the table changes later, your statement is still clear and safe. Keep data types aligned with the schema. Numbers for the ID, text for the name, and email. Next, we will read the rows we just inserted. This cell runs a select statement and then converts the result to a pandas data frame so we can see it in the notebook. You will see 2 rows with the exact values we inserted. A few habits for querying. Use select star only for quick previews. In real work, name the columns you need. That keeps results stable and fast. Add a where clause to filter and limit if you only need a small sample. Keep 1 select per semicolon so your results are easy to read and debug. In this section, you see 2 ways to do the exact same thing. Create a table, insert a couple of rows, and read them back. Cell 1 uses the SQL magic, written as %%SQL. When a cell begins with that header, everything inside is plain structured query language. We create a table named products with 3 columns. Product identification as an integer, name as text, and price as a decimal number. Then we insert 2 products and run a select to preview the table. This style is perfect for teaching, for quick exploration, and when the whole cell can be written directly in SQL. Cell 2 does the same steps through Python with the connection object. Here we call connection.execute and pass a multi-line string that contains the same structured query language statements. Think of this as the programmatic route. It is handy when you want to build queries from Python variables, loop over data, or wrap several statements together before you run them. CRUD stands for create, read, update, and delete. These are the 4 things we do to rows in a table. Create, inserting data. In the first cell, we add new products. We name the columns, product identification, name, and price, and then list the rows we want to insert. Good habit. Always list the column names in the insert statement, so the meaning stays clear even if the table changes later. After inserting, we run a quick select to confirm the rows were added as expected. Read, querying data. The select cell simply shows the contents of the products table so we can verify results. For quick checks, select star is fine. In production, name the columns you need so queries stay stable and fast. Update, modifying data safely. Next, we change the price for one specific product using a where clause on the product identification. This is the safe pattern. First, run the same where clause as a select to preview which rows will be affected. Then run the update. You will also see a second update example that does not include a where clause. That would change every row in the table. It is shown here as a warning. In real work, do not run updates without a where clause. When in doubt, use a transaction and be ready to roll back. Delete, removing data safely. We delete one product using a where clause on the product identification, then select again to verify the result. That is the safe pattern for deletes as well. Preview with a select, then delete with the same where clause. There is also a delete example that removes all rows from the table. This is dangerous and rarely what you want in a live database. Use it only when you truly intend to clear the table. Today you learned the big picture and the first moves. A database is the data. A database management system is the software that manages it. Relational systems use tables and keys. No SQL systems trade rigid structure for flexible schema and scale. Reliable databases follow ACID, atomicity, consistency, isolation, and durability. Structured query language has 4 roles. Query with select, change with insert and update and delete, define with create and alter and drop, and control with grant and revoke and commit and rollback. Keep syntax clean. End statements with a semicolon, write keywords in uppercase and identifiers in lowercase, and use clear aliases. In practice, follow the CRUD loop. Create rows, read to verify, update carefully, and delete only what you intend. Always preview target rows with a select before any update or delete, and use transactions so you can roll back. In our notebook, we used DuckDB and JupySQL, so you can run real queries right where you analyze. Next time, we will add filters, sorting, grouping, and joins to answer richer business questions.